All right. Okay. So here we haven't discussed all the cases yet. So we have discussed the explicit algebraic formulas and explicit or unsteady ODEs, right? So let's actually another case is when we have implicit functions. So that's something that often appears. For example, if you have a steady state PDE, Poisson's equation, and you discretize it, what you get is an algebraic system, but it's implicit, right? So what if we have J as a function of U, but U is governed by a f of, let's keep writing as G, right? So G of U and S is equal to 0, where there is an implicit relationship defining how S influences U. So here, what do we do? Actually, there is a, if you think in similar to, like, if you think in the first approach, right? So beginning, we discussed the two approaches. One approach is just to keep substitution. That approach, it's a little bit difficult dealing with the implicit case. But once you look at the approach of Lagrange multipliers, there is essentially no difficulty in treating this. So first of all, you still linearize delta J is equal to partial J partial U times delta U. And you linearize this relationship to be partial G partial U times delta U plus partial G partial S times delta S to be equal to 0. And you can do the Lagrange multipliers with no problem at all. So I'll just add U hat transpose times partial G partial U times delta U plus partial G partial S times delta S. Right? Because this is equal to 0, I can multiply it with any U hat. That is 0. I can add it to delta J. Alright, so the task is just to cancel this term with this term. So manipulation, partial J, partial U, plus U hat of J, partial G, partial U, this whole thing times delta U, plus the remaining term that does not depend on delta U. Right? So here the adjoint equation is that. So the adjoint is partial G partial U transpose times U hat is equal to partial J partial U transpose. You would solve this adjoint equation, which is now a linear differential equation. Linear matrix equation, right? And then you substitute the adjoint solution for computing the gradient dj ds, which is U hat transpose times dg ds.